Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. Today we have a good friend of mine on the podcast, Owen. Thanks for taking the time, man.
Yeah, for sure. I'm excited.
So Owen wrote this really interesting Foundry plugin to deploy straight out of Foundry onto zkSync, the layer 2. So Owen, why don't you really briefly introduce yourself? Why did you have to write the plugin? And then let's straight jump into the code.
Yeah, for sure. As a developer, I was working in the Web 2 space for a while and just jumped into kind of the Web 3 space during the NFT boom. Got into that, did some ETH Global hackathons, and haven't really looked back. Been working in the Web 3 space for about a year and a half, 2 years now. Mainly started off in front-end development, but in the last few months, kind of half a year, really looked more at smart contracts and more like infrastructure stuff. I love doing stuff with the subgraph or like data layer stuff. But yeah, kind of just starting to become more well-rounded. With this zkSync plugin, I've been working recently with a project that is deploying to zkSync called Increment. Through that, I've kind of been toying with them for quite a while now. And I noticed that when I went to create a repo that I wanted to build smart contracts and deploy them to zkSync, I wanted to use Foundry, but at the time zkSync had no Foundry support. And still right now, this plugin is kind of the only Foundry support at the moment, and it's unofficial. But yeah, I kind of wanted to bridge that gap, and it was kind of a fun challenge. I did a majority of it in a weekend, and then kind of worked on it since then. But yeah, I would love to kind of show it off, and you can learn more about zkSync and the deployment process.
Yeah, for sure. And love your hat, by the way. I didn't even notice that before.
Thanks. I had to throw it on, and I got it in Denver, but yeah.
For sure. No, zkSync is interesting because it's in this gap between EVM equivalence. So zkSync is EVM compatible, right? Which
Yes.
means it can take some high-level languages like Solidity or Viper, but it doesn't compile that into EVM bytecode, but actually compiles that into some zkSync VM bytecode. Is that right?
Yeah, exactly.
Okay.
Yeah.
And that's where the difficulties come from. And that's basically one of the main reasons, I think, why you would have to write the plugin itself, right?
Yep. Yeah, and I'll kind of show you the differences there for deployment as well.
Awesome. Then let's go into the code.
Cool. I'll kind of start off with, once you can see my screen there. Let's continue on that topic there. The contract deployment. A majority of zkSync's EVM is very similar to sort of mainnet, but the main difference is that when you're deploying a contract, you call a function on to an address rather than sending the bytecode to the zero address with the constructor variables. And so you have to call this create function on the contract deployer, which is a system contract. With that, you also have to pass in these factory deps, which are the contract bytecode. And then that is not stored on-chain, but the hash of your bytecode is stored on-chain. So that's kind of the main difference there. Rather than deploying to the zero address, you deploy to this contract, and you call the create function. Other than that, a majority of the process is similar. So we can take a look at first. Let's see maybe how we use the plugin that I built. So I have it kind of outlined in the README. It's fairly simple. You have to have the daemon proxy, which is the mainnet address for the bridge. I should actually back this up. Sorry. For deployment to zkSync, since there is that difficulty of factory deployment or factory depths that aren't on chain, deploying from layer 2 right now is not simple through Foundry, because there's a different format that you have to send the ETH send transaction call with. It's not exactly doable at the moment with Foundry, which is why for this plugin, what we do is we deploy from mainnet through the bridge and call that create function on L2. So this is why we kind of need this mainnet daemon proxy. This is just one address for all the functions that they have on mainnet on their bridge. We pass that into a deployer function with the compiler version. And then with that deployer object, we can deploy our contracts. So we can call deploy from L1 the relative path to the contract, the parameters for the constructor, as well as some salt to get a deterministic address.
Okay, because we're using create2 in the background.
Yeah.
Okay.
Before I continue, I kind of just went through quite a bit there. Any other questions that we should cover first?
So yeah, this is basically like the interface that you would use as a developer if you wanna use Owen's plugin. It's interesting that you have to do it through L1, right? Which of course has some disadvantages, mainly gas, right?
Yeah.
Which is
for sure
is the main factor here. But other than that, I love how simple the interface is.
Yeah, I wanted to kind of make it as close to a normal deployment of a contract as you can. But obviously there are some differences with Foundry here that we can't really use.
Yeah.
Another thing to note here is that I use FFI for a lot of the process because we have to use that custom compiler. We pass in the contract path, and it passes back our bytecode. So interacting with the console through Solidity with Foundry can be done through the FFI cheat code. So you just have to enable that, as well as read-write permissions in your project. Then let's dive into that deploy from L1 function in the constructor. So when we create that deployer object, we pass in, or we get the project root using a cheat code, and then we actually install the zkSolC compiler. zkSync has all the versions of their compilers available at a repo, which I store in the constants file here. zkSolC bin, they compile all their binaries for different architectures and store them in a repo there. So what we can do is then call install compiler, and this is kind of the first time that we use this FFI. What we do is we grab the system info of the user, which we have to do through FFI as well, which is a little hacky. But basically what we do is we call some functions, or call some CLI commands, see if they work. If not, then we can assume that they're on a different machine. So basically we just echo process architecture and determine whether it's Windows or Windows, then it'll be AMD, EXE, and these other things. So this is just to kind of find the right path for the compiler for your machine. Then what we do.
Let's summarize for a second, because I think that's already super interesting and just shows how powerful Foundry can be, right? So FFI, if someone listening doesn't know, is I don't know what it actually stands for, like foreign function interface or something like that.
Yeah, I'm not actually sure.
Yeah, me neither. It just allows to call external programs. So you step outside your Solidity world, do some things, and get back an output, right? And what Owen is using this for is to actually see which is it Windows or Mac, and then the actual CPU architecture that you have to actually compile the correct zk compiler. The correct zkSync compiler, and the zkSync compiler is totally different from the normal Solidity compiler, right?
It's totally different, but it does use the Solidity compiler as well.
Okay.
It's kind of a layer on top of it.
I see. But okay, that's interesting because I think the zkSync compiler is written in Rust. So I thought it's just a totally different beast, but okay, it's calling the Solidity compiler inside.
Yeah. But yeah, we assume that the user has solc in their path, and then this binary will just kind of go with that and make that assumption as well.
Cool.
One thing to note there is that we don't actually compile the zkSync zk-solc compiler. They have those binaries available. So we just download the correct version.
Yeah.
So that's what we're doing here. We create the path for that Git repo and the correct artifact, and then we just download it with curl and store it in the lib folder. We also use the chmod here just to allow it to be executable. And then we can continue there.
Okay, so actually, maybe a better name for the install compiler would be download compiler, right?
Yes. Yeah, that's probably a good idea.
Okay. If anyone wants to do a pull request, Owen is open to anyone to contribute.
Be super happy to see any contribution. Cool. And that's basically all we do in the constructor. We just download that compiler. We also set the daemon proxy, but that's pretty simple. Cool. Once we have that deployer contract deployed, it won't be deployed during your script, but it's just kind of used for Foundry. Then we can call the deploy from L1, which we have that file name, parameters, and salt. We also have this deploy from L1, which just sets our gas limit and L2 gas per pub data byte limit. It's a long name. Last time I checked, these were kind of just constants still, and the hard hat plugin that zkSync provides just uses them as constants. So I store those in constants and just set them by default. And then we get into kind of the fun part. So first of all, we have to compile the contracts using that zk-solc compiler. Since Foundry doesn't have any support for alternate compilers right now, just just solc, we have to do it using that FFI command. And we do that within the compile contract function. And so here we just pass in the zk-solc path that we downloaded, set the bin flag, and then pass in that file name, which we passed into the deploy from L1. And that file name will be like src/contract, whatever. And we'll just grab that relative path. Then what we can do is we get that compiler output, which in this case is where Foundry's FFI plugin is a little bit tricky to work with. One of the things that Foundry does, so it will try to assume that the output from the CLI command that you wrote will be in bytes. If it can't parse those bytes, then it will return it as a string, as like UTF-8, which is difficult because it converts that bytecode that this compiler output into a UTF-8 encoded bytecode, which is kind of annoying. And this is simply because the zkSolC compiler outputs a prefix to the bytecode. It'll say like it says bytes : and then the bytecode, which causes Foundry to parse it as UTF-8. So
that's an interesting behavior.
Yeah.
Because my intuition would be you try to parse it as UTF-8, and if that doesn't work, you return bytes.
Yeah, that's true. But yeah, I mean, there's some cases where I kind of wish it just did one or the other, and not kind of flip. I've used it before too. I was trying to get the gas price of the block using, I think it was a cast command, and every once in a while it would actually read it as UTF-8, even though it was bytes. So it was kind of unreliable, but for this case, it will always parse it as UTF-8 from my experience. So to solve that, I use this strings library and split it at the space, just to grab that bytecode encoded as UTF-8. And then what we can do is we can actually just echo it. And since Foundry will successfully parse it as bytes this time, it'll just be that bytecode without that UTF-8 encoding if we just echo it, which is, again, kind of weird, but it works.
Okay, so that's a trick basically to use FFI to get the bytecode. So you echo it in the terminal or something and grab the output.
Yeah, exactly. So if it's UTF-8 encoded and you don't want it UTF-8 encoded, just echo it again, and it will get it that time.
Okay.
There's probably a much better way to do this without using the echo, where you just figure out the UTF-8 conversion in Solidity. But I didn't bother figuring that out for now.
To be honest, that really sounds like a good idea for an external library to do that stuff.
Yeah, no, and actually, when doing this, I tried looking for a lot of libraries for conversions, because there's so many different conversions that you need to do when using FFI. Like if you're converting, I guess it's mainly UTF-8, but there's some other ones too. And I couldn't find too many solutions out there, just because I guess most use cases don't really require it. But yeah, it would definitely be a cool external library.
Yeah.
Cool. Once we have that contract compiled, we have to get the hash of it that we are going to put on chain on L2. And this requires a bit of configuring. That their hash is not just a simple Keccak 256. I think you parse out the last few bytes, and then you do a few different things, which I don't really want to go into. But zkSync provides a L2 contract helper in their era contracts repo, and this basically just allows you to call. I think it's on the other one. They have two different directories, Ethereum and zkSync. And so if we look into, I think it's zkSync. Let me just double check. Ethereum contracts library, common library.
So this, what Owen is showing right now is basically like helper Solidity files provided by the team behind zkSync, right?
Yeah, exactly. So yeah, they have a hash L2 byte bytecode, which you just pass in that bytecode, and then it gives you back the correctly formatted hash,
Okay.
which is nice and easy. So yeah, then we have the bytecode and the bytecode hash. We also need to encode the call to the contract deployer. So as I was saying before, instead of deploying to or calling the 0 address like you would on mainnet or some other EVMs, you have to call the create function on the contract deployer system contract. So what we have to do is we just do ABI encode call. The contract deployer, I'm using create2 just because then we can get the correct address out and print it in the logs. Create2, the salt, the bytecode hash, and the params. And so we can take a quick look at that contract deployer. Actually, I have it. The interface described here. They don't actually have the full contract deployer contract. I'm guessing because it's a custom like non-solidity implementation. But they have this interface iContract deployer, which has create and create2, I believe, are the two main functions. But yeah. And then we encode that create function, create call, on the contract to call to the contract deployer. And then we also need to send that call data to the bridge to execute on L2. So we're going to grab the mailbox here. We get factory dependencies, which is, if we go back to the differences here, factory dependencies are the bytecode, the contract's full bytecode, not just the hash. So we just set that in factory dependencies. Base fee, they also have a helper function for this, which just gets L2 transaction base cost. They just do different fees on zkSync. So you pass in the mainnet fee and then these two constants that we had. And then we get that base fee.
Again, I think that's interesting too. Again, a difference between EVM equivalence and EVM compatibility, that you have different gas fees for different opcodes, right? Because I think for EVM equivalence, it's equivalent, if I'm not mistaken.
Yeah. So actually, the thing with zkSync, which I think really sets them aside from other zk EVMs, is that they only publish state transitions. So you can save tons of gas for frequent transactions or like common transactions. So like, let's say their Uniswap deploys on zkSync and they have their ETH USDC pool. And then I buy USDC, you buy ETH, I buy USDC, you buy ETH. Instead of pushing those 4 transactions onto mainnet, they just check the one difference in balances and state of the Uniswap pool, and they'll publish that, which is one of the main differences there. As far as I understand, like Polygon zk EVM, they push all of those transactions there, but they have the benefit of visibility. Like with zkSync, you have to kind of parse and figure out what happened using their data. Whereas like Polygon zk EVM has it available right away. But yeah, there's little nuances that kind of make it a little bit different. But yeah.
Okay.
Cool. So yeah, that's another helper function on that L2 contract helper. Actually, no, it's on the bridge itself on mainnet. So we can just call that. And then finally, we call the request L2 transaction. This one we're calling on the bridge to send that call data to the contract deployer. So we're going to use that L2 system contract address. This is the contract deployer. We're going to pass in the L2 value which is just if you're going to send ETH on, it's the same as sending value here, but the value that gets transferred to L2. Encoded deployment. This encoded deployment is the call data that we created, the create2 call with the salt, the bytecode hash, and the params. The gas limit, which is just the same as we've used, that constant there, as well as the L2 gas per pub data or pub data byte limit. And then the factory depths. This is the main reason why we can do it from L1 and we can't do it from L2. Because this factory depths, which is the bytecode for the contract, gets published to L1 using this method. When we call this function on L2, like here, the encoded deployment function, the create2, we only pass in that bytecode hash. And if we're calling this function directly to L2, we use that custom transaction format that they have, and we send the bytecode there, the full bytecode there. So it's a difference that allows us to do this through L1. And Foundry's...
Yeah, to be honest, I didn't fully understand. Could you go through that again?
Yeah,
I think sure. That's the really interesting part here.
Yes, yeah. So, just to recap, this factory depths is the full bytecode.
Okay.
This bytecode hash, which gets posted in the transaction data on L2, is a hash of the bytecode, but not the full bytecode. When deploying from L1 to L2, we can pass in this factory depths on-chain. When deploying directly from L2, we don't post that in the call data. We post it in a different part of the ETH send transaction.
I see. Okay. So the layer 2, zkSync layer 2 has a special transaction format which isn't supported by Foundry, and that's why you have to do it this way.
Yeah.
Okay.
And to clarify, that special format is not required for anything other than contract deployments. So specifically for contract deployments, because we need that factory depths, we have to use their format. Everything else we can just call normally with an RPC.
Okay.
A standard RPC 1559 type transaction. I think that's correct. EIP. I'm going to go into that after too, just so we can take a look at kind of the future of how I want to do this with direct L2 transactions. So we can take a look at that formatting after.
Awesome.
But yeah, so this, we pass in the full bytecode and then a fund recipient. I believe this just is the recipient of the value, but I'm not entirely sure. We also have to pass this value here, which is basically the fee to this encoded deployment call. I add a little buffer in there because sometimes when it gets passed over, the fees will change, and there's a difference between when it's executed and when it's sent. And then we can get the params hash, and we can get the create2 deployment address. So we deploy in this function. This goes from L1 through the bridge. The bridge tells on L2 to call the deployer create2 function, and then it will deploy our contract there. Since we use create2, we can compute the address deterministically. So we just pass in a hash of the params, deployer, salt, and bytecode hash. And so that's it. Then once you run that, you'll have this deploy from L1 will return the contract address of that deployment.
That's so cool. Like,
yeah.
I think So it's a small script, but very dense, right? So we touched on on different compilers, on L2, on transactions on layer 1 that actually trigger contracts on layer 2. So yeah, oh no, super interesting, man.
Cool. Yeah. Maybe I can go into kind of what I want to do for the future of this plugin. The main thing obviously is deploying from L2 to save gas, and it would just be kind of a better user experience.
Mm-hmm.
The issue there that we kind of talked about is that there is a different format for transactions, and zkSync calls this their EIP 712 transaction, which I think is a little bit confusing, just because when I think of EIP 712, I just think of signing typed data. But they use this as like a type transaction. And so what this is, in addition to the normal ETH send transaction where you have like gas fee, call data, or like data, recipient, or like sender to from, those kind of values, you also have gas per pub data, custom signature, which is this EIP 712 signature, paymaster params, and factory depths. Paymaster is something else that allows you to pay with fees, pay for fees in some like a different token rather than ETH. We don't have to cover that. But this factory depths is the additional parameter that we need to have to deploy directly from L2. And this custom signature here is just a EIP 712 signature of this following data structure, which is transaction type, the EIP 712. They have a constant for it. I think it's 113. From to gas limit, gas per pub data limit, most of the standard ETH send transaction parameters, in addition to paymaster, and that factory depths. This is kind of what we would need to be able to deploy to L2, and the way we would do that through Foundry, hopefully, would be to have kind of a generic send call. Maybe have a cheat code that would allow you to pass generic values to a ETH send transaction kind of thing. Because we can sign this using cheat codes already. We can do a sign type data function through Foundry, and we can format all this data. But sending it through that ETH send transaction, there's no support for that currently with Foundry, which I'm not super into the Foundry code base. I don't know a whole lot, so I don't want to kind of mess things up there. Maybe they have a good a good roadmap for kind of keeping things clean. I don't want to make it too messy, but I would be excited to kind of know what the path there is, and kind of figure that out with the Foundry team. Just recently started like open an issue to kind of track this, but yeah, still in kind of the early stages, and there's a bit of changes that need to be done for this. Yeah. Although what could be done, as we saw before, is using FFI to call that ETH send transaction. With Foundry, you can grab RPC URL from the M, and you could theoretically just call that using a raw like HTTP call through the FFI, but that kind of loses out on some things like broadcast logs and other things that really integrate with come with the Foundry ecosystem, which make Foundry nice. So that would be a very hacky way of doing it, but it might be kind of intermediate step that we could implement to just allow that somehow. Yeah.
Yeah, it doesn't sound like an easy change to Foundry, right? But I think it could be very important because you will not be the only one to run into this issue, for sure.
Yeah.
And that's the interesting discussion right now about the trade-off in the zk EVM space, right? You have some people who go through the path of total EVM equivalence, right? Which means here's my EVM bytecode, it's totally the same. And then there's something like zkSync, which I think is at an interesting spot because you can still use your Solidity, your Viper, but internally it isn't compiled to EVM bytecode. It's something different, which will have some, especially security tools that just don't work anymore, right? But at least you have your high level languages that you still use. On the other hand, you have something like Cairo, right? Which again, totally different language, totally different bytecode. On the other hand, it's the fastest proving time, I think. So that's the trade-off between, okay, you stay near to the EVM, but your proof time, your ZK magic stuff is really slow. But on the other hand, you have something like Cairo, which is totally different, but the ZK stuff really works. It's really fast.
Yeah, I've seen a lot of debate on Twitter about that. It's very interesting. Like I think they are kind of two different realms. One that will help onboard a lot of people into the zkSync ZK ecosystem. Although if they're stuck in the EVM, I don't think they'll learn too much about zero knowledge in general. But on the other hand, if you dive into Cairo and you get to learn all these proofs, and it's a very eye-opening new things that you can do with that. But there is a big jumping off point. You don't have your comfortable EVM anymore. Yeah. So it'll be interesting to see what happens. I think they'll kind of create two different paths, but in the end, still benefit the ecosystem overall. So.
No, for sure. I just think it's with something like Cairo, right? Really hard for mass adoption, right? Yeah. If you come from something like Solidity, which is like, I don't know, JavaScript, Python, C++ on this level, and you switch to something like Cairo, it's a very, very big learning curve. So I think that will, I don't know, I'm kind of skeptical personally here. But I think on the other hand, the total EVM equivalence is just really hard to do. So that's why I like the zkSync spot right now. I think it hits a good spot right now at this moment in time.
Yeah, for sure. Also, it seems like the community, or in general, people are excited about it. With their first 6 days, they had over 60 million TVL, which I think is still below their zkSync Lite. But compared to something like Polygon's zk EVM, I think they only have close to 1 million or a bit over 1 million. And they launched 2 days after. Which it's kind of exciting for me, at least. I enjoy the ecosystem quite a bit, the zkSync side of things. So it's cool to see that support there. And hopefully it'll continue to expand there.
Yeah, for sure. I don't know, man. Do you have anything other than that interesting? I'm open for. I know I love these discussions, right? Compilers, layer 2, ZK stuff. So if you have anything else interesting that we can talk about, we still have a few minutes left. let's do it.
Yeah, for sure. One other thing that kind of jumped into my head when you were talking about the different languages, zkSync, when they released their full organization on repo, they kind of publicized all their repositories. So I digged into there. One of their projects that they have is a plugin for the LLVM. I think that's yes, yeah.
Yeah, I've seen that. That's a really good point. Yeah, go ahead.
Yeah. So if you wanted to, like LLVM is a big tool chain for compilers, right? So if you wanted to develop a language that like Rust and compile it to zkSync EVM, you could do that very easily. I mean, I'm not familiar myself with the whole compiler space.
I don't think it's very easy, but I know what you mean. So how LLVM works is LLVM is huge, right? So this is a very, very big simplification. But you basically have a front end and a back end. And what you do is, so basically you have, for example, you have a Solidity, a C++, a Rust front end, and you compile that into IR, intermediate representation, which is basically like LLVM code. That's how I understand it. And then you can take that LLVM IR code and actually compile it to the thing that you're targeting. So in this case, the zkSync VM bytecode, right?
Yeah.
So this allows you that, for example, the zkSync team can focus on the back end, and other people can write or any other front end, right? You could do it Solidity, C++, C, Rust, whatever you want to do.
Yeah. Yeah, I think that would be very interesting. I think that, like, for sure there would be some security concerns that would pop up there. Like how do you verify? I guess you could try and do it through formal verification, but that's definitely a big problem for that kind of direction. But yeah, I think that would be interesting. I mean, I personally don't think Solidity is the best language for smart contracts. Like, I'm not super familiar with it. I'm not a Solidity everyday kind of guy. So I would be interested in seeing kind of other languages be developed. I do enjoy Viper. Like, I've used Viper in the past. I'm also not like, I didn't start out with Python. I'm not a huge Python nerd. But I do kind of like that formatting. I think it's really nice. Yeah, I think there's things that can be improved, but the developer ecosystem is at a point where kind of you wanna find something and stick with it.
Yeah.
So yeah.
Let's say this. Per definition, there can't be like the perfect language for anything, right? I just think that Solidity is good enough. Okay, my personal point of view, and the network effects are just too strong at this point.
Yeah,
look at JavaScript. What did we do with JavaScript? We took JavaScript as it is. It won basically the network effects, and we optimized the shit out of the JavaScript VMs. Right? Yeah. This is what we did. And I have the feeling the same thing is going to happen to Solidity.
Yeah, that's a good point.
And I even think, Owen, that the network effects for smart contracts are even more extreme than for JavaScript because of security.
That's a good point.
I think it just, it would cost too much to switch at this point.
Yeah, and when you think about like all the different plugins, like Echidna or, that's the only one that comes to mind right now. But
the tooling The tooling is look at the hard hat to Foundry. Who knows what we'll have in a couple of years. The thing is, if your security tools mainly focus the EVM bytecode itself, it doesn't matter which language you write it in. But I don't feel we're at this point right now. But maybe in the future, maybe in a couple of years, it doesn't matter if you write Viper or Solidity. In the end, you look at the bytecode, but I don't see how you would audit EVM bytecode directly, right? It's not really possible.
Yeah.
But yeah, exciting for sure. Let's see what happens.
Yeah, for sure.
Awesome, Owen. Then
cool.
Thanks for taking the time, man. Really, really interesting tool. I think with all the zk hype that is happening now, it's at the timing is really good, I think. And it has already, GitHub stars, you can criticize it, but it's some indication, right? I think it has over 60 stars for a Foundry plugin for zkSync, which I think is amazing, right? If this was a web front end, it's equivalent to 20k stars, I think.
Yeah. Thanks. Yeah. Also, thank you for having me. I'm really excited about this format of podcast, and I think you're doing great as a host. So I'm excited to keep seeing these come out.
Thank you.
I'll be keeping my eye out.
Really, really appreciate it. If people are looking you up, where can they find you? What are some other interesting things that you're working on?
Yeah, for sure. I would say I'm probably most active on Twitter. Just Omurovec, Omurovec.
You need a better handle, man.
Yeah, probably something a little bit easier. But yeah, you can find me there. The main project I work on right now is Increment, which is doing perpetuals using Curve as a trading engine on zkSync. So we're planning to deploy fairly soon. So keep an eye out for that. It'll be kind of fun to join in the zkSync era ecosystem, and we'll have another thing to play around with there. But yeah, check me out on Twitter. Sharif, if you want to add the GitHub repo in the description, they can check it out there, and feel free to submit an issue or a PR, and be happy to see any activity there.
For sure. I'm gonna link everything in the description. Repo is 100% open for pull request if you have something interesting to add, or even if if there's a interesting discussion to be had, open up an issue or something. I think that would be awesome.
Yeah, for sure.
Okay. Thank you, guys. Thank you, Owen. This is definitely not the last episode we're going to have with Owen. This is only the first one. So I'm looking excited for the future project that you're going to work on.
For sure.
Nice.
Cool.
See you in the next one. Bye-bye.